does it list? Okay, so if you go to live, okay, it just says streamed 1 day ago, streamed 3 days ago, 6 days ago, but they do not. I mean, how do you, like if I did the one that was 8 days ago, does it actually have the date outside of what I did in the stream? And I don't see the date. It just says eight. What if I say show more? What does it say? Okay, it says stream live on March 29th. Okay. It'd be great if that was listed in the header part, but anyway. Okay, so let's do something weird that encompasses everything in impact. Okay, so the question is, and this may take 2 periods to do. Question is, can you cheat at pool? And if so, how? So, this is a weird question to ask, but let's say in pool, from a top view, somebody is hitting the ball with a pool cue, and the ball is traveling and it hits another ball. So let's take the case where this one travels here and it's hitting this one, and the goal is to make it go that way and go into the pocket right there. So eventually, this thing, I'll work the problem simple first and then I'll complicate it next time. But we're just going to find out, can you cheat and how you would cheat. That's probably not a thing that I should do. So you come up and you're going to want to make it so you hit the ball right there. Now, the question is, really, if you go straight off to the right, if you do oblique impact, if someone does this, can they change the path of the ball, or do they just change the speed? And so what we'll do is we'll do this problem this way, and we'll say this is the impact. We may have to ask this question about another scenario to find out if we could, how this would affect the game. So this is the impact plane, and this is the line of impact. And so the first thing we're going to do is we're going to say this is ball A and this is ball B. So during the impact, nothing is going to happen to, as far as nobody's going to stick their pool cue over here and hit it. Back here over time, you've got the ball going from that impact, but then it has a velocity right here. So let's say the velocity is 4, 3, and 5. And yeah, we'll just make it feet per second. I'm not going to worry about the true mass of the two balls, but what I'm going to do, I'm going to say the impact equation, the first equation, MABA, and I'll say I equals before impact. I'll say this, I'll say just before impact. And then F is equal to just after impact. So we do that. mass B, BB just before. There are no forces external during the impact. So what you have is MA, VA final, or just after impact, plus MB, VB final. But this equation will apply along the line of impact. Let's see if this will come up and remember where I was. In the last video, let's let this one come up. It might, I doubt it'll go back to exactly the same place. Okay. Click it again. Okay, wait. Well, I guess maybe I shut it down here. Let me go back into here. That's interesting. I thought I had it up. Maybe I did shut it down. So I was doing this last time, and I got to this equation in the last lecture. Let me get down to it. Okay, so here's this. Okay, this one. Maybe I can kind of remember. So what we had, I guess it won't move over, so I guess I just have to work with it like it is. You know what that hand does? Well, the hand just makes it so I move it around. Is there a way? What does that do? That doesn't do anything. Oh, maybe I can move it over here. Okay. No, I just want to move that over there. Can I take this? No. Yeah. That won't let me move it over. So anyway, this is an impact that occurs where you have the plane of the contact and the line of the impact. And what he does is he breaks it into components. So he takes the X component and the Y component. And this one, and that one. But during this, so if we did this, okay, so here is A and here's B. It turns out that if you look at this, these two are, I should say, equal and opposite. So these are equal and opposite. Then what you have is if you stare at this for a minute, hang on, and just look at A. We'll look at B in a second. So you just look at A, and then you're staring at it and you're saying, I know this is here, but I don't care about what its value is, but I'm going to write the equation about it. And what you'd see is MA BAX1 plus, and I'll just say integral F through T because it's along the line of impact, equals to MA VAX2. So you had this causing a change. If in fact, though, if in fact you were in a position where you were looking at the Y component, you would realize that this is only in the X, this is only in the X, this is only in the X. So what you would find out about the Y component there is that this value right here is equal to this value right here. Meaning, meaning that the Y component of A before is the same as the y component of A afterward. If you do the same thing here and look at B, you'll conclude the same thing. So in other words, look at the x here. You got this. I'm sorry, the y. This equals to that. There is no force here or this direction. Since there's no force, then you're just saying this term is equal to that term. What you're saying for the x component is this term and this term together has to equal to that term. There is a force here equal and opposite to this. It only occurs along the line of impact. So what happens is this is along the line of impact. So if that's the case, and you decide you want to call this, and generally people do that, call it x and y, then you would technically want to put an x, and x. Now what you'll find for the y is MA VA Y I equal to MA VA Y F. So then it's like these are boring equations. They don't really get you anywhere. So you end up with something like that because what you're trying to do along the line of impact is you're adding all those. So here's what you're doing. You're saying on the left-hand side, I'm going to take all these terms. This is the system, A and B. But this cancels that. And so that's gone because it cancels it. So that means you've got this together with that is equal to that together with that. And that occurs along the line of impact. What binds these two together is that force. So now let's go back and let's work in there. So what we find out is, let's say this one's at rest because the ball's got to come up and hit it and make it go to the right, or you hope it does. So VAXI is equal to 4, and that 4 came from here. Although this is 5, that actually is 4. Then VBX initial is equal to 0. So the ball is sitting still, not doing anything. Now, I'm going to leave this as a variable, and this is a variable right now. So MA, or 4MA, so I take this, I stick it here, and I get this. Then I take this and stick it here, and I get 0. So, the left-hand side only has that. And then you have this, VAX final, plus MB, VBX final. Now, if you had, and let's just for temporary, we'll say, just so that we can make things simple, equals to 1. And this is kind of weird, but it doesn't really matter what the value is because if they're both equal, they can all cancel out. So it can be just any number. And so your equation there becomes 4 is equal to VAXF plus VBXF. And you're kind of done there for a moment. Problem is, you have 2 unknowns and 1 equation. But, you know, last time I kind of mentioned this coefficient of restitution, which, and so you might want to go back and look at that one because that one I looked at, what I did in that lecture is I looked at, and actually it was an okay lecture. I thought it was okay. It kind of formed on its own. I looked at this problem and kind of went through it just a little bit, and then I went through this problem. And there's two aspects of these two problems that just so happen to make them interesting. The one aspect of this one is that they stuck together after they hit each other. So they were coming together, then they stuck together. They had a common velocity. This is what you might call a plastic impact. And what we find out in a minute, or in that last lecture, we found out that was a coefficient of restitution of 0. Then the next problem was one in which he claimed that no energy was lost during the collision. And if we claim that, then he goes through all these equations here using energy equations. He doesn't show it, but later I basically showed that the coefficient of restitution was 1. And what the coefficient of restitution is if you, I guess I'll have to slide down till I get to that page. It's the next section. So what happens during an impact is kind of interesting. You have before impact, you have during the impact where it's squishing together or the deformation. Then you have a point. So this could occur over a delta t. This will be at certain t, I'll just call it question mark. At certain t, this occurs. This is like a state. And this occurs over a delta t where they're coming back apart, or restoration. He calls it restitution impulse. And that's this and this. So he calls the P force, the force amongst these two as they're deforming. The R is when they're restoring back to their physical state. And what will happen is these are always, when there is an impact, there's some sort of deformation there, even though it might be small. So what he does is he starts by looking at the system this way from here to here. And he says, hey, this is what we've got overall. And then what he says is, hey, let me just look at A, for example. So he looks at A, what happens at A. So if you're focusing in on A, what you see, get rid of all this mess. You're looking at A only. Then you say, oh, during A, it's deforming. And so there's some sort of force. This part isn't really considered because that's a point in time state, a certain time. This one is the restoration, and then we end up back here. So what he's going to do is he says, hey, wait a minute. I've got this. So I go from here to here. This particular spot is right here. So in other words, he does the impact from here to here to here. And we have that P force. And then he goes from here to here to here. So if you look at it, you're actually going from here to here, but you're going in two sections. You go through that first section, which is that. This is the maximum, what do you call it? Maximum something, deformation. Then he goes from the maximum deformation to the final state. So he went from here to this one, then from this one to this one. Then he says, hey, let's put these two together and divide them, and you'll get this funny equation like this. And then you're saying, okay, so what? The coefficient of restitution is 1 if these are 0 if they're kind of in a plastic state. But how do I get rid of this and that? Except I turn towards B, and I do that, and I get these two equations that are both the same thing. And then if you start equating these and working all this out, you'll get a coefficient of restitution of this. So if you look at last lecture, you'll see how that kind of built. But what I'll do is I'll do an additional thing. So how would that look? So if you had a coefficient of restitution, of a certain value. Let's say VA dB. So this is another thought or a problem. It's not the one up there. And this is only, I'm only doing this. Okay. Okay, so this is the final initial. Okay. Wait a minute. No, here. Okay. So his 1 is the initial and 2 is the final state. And notice they're changing their sequence there. But let's see if we can make common sense of this by looking at something you've seen before. You go out and you play tennis, and you take your tennis ball and you drop it, and then it only comes up about an inch, and you say, I'm going to throw these tennis balls away. They're no good. So the question is, what's the coefficient if you drop it from 6 foot and it returns a half a foot? Okay, so here's the thing. The impact occurs between the earth and a tennis ball. So it is true, you could go in here and look at M tennis ball, V ball plus M earth, velocity of earth. But the fact that that tennis ball hit the earth, the masses are so big that it didn't change the velocity of the earth. So using that equation doesn't really get you anywhere. Here, I'll go ahead and, so this is before impact, the velocity of B. Anyway, so this doesn't get you anywhere. So what gets you somewhere is the coefficient of restitution. So let's say you drop it from 6 foot. It doesn't really doesn't matter what the mass is, but we'll. So if you drop it from 6 foot, it's at rest. 1/2 mv squared equals to mgh, where h was 6 foot. The m's cancel. So what you get is, hang on, let me go down here. Let me just use this as a variable. You get v is equal to square root of 2gh. You get the g and the h. You get the 2 coming over. You take a square root. So that would be the velocity if you dropped it from 6 foot. So let's say, what is that? 32.2. The h of 6 foot, then the velocity is equal to, and I'll use this thing. Let's see if it'll recognize that as a 2. Okay, and that is 19.65. Okay, so that's the velocity. So the situation is just before impact, it's going 19.65. Just after impact, it's not going 19.65. It goes up a half a foot. So therefore, the velocity is equal to 2gh. The equation doesn't change, but it's 2 times 32.2 times 0.5. And that becomes, here, I wonder what happens if I can do that. Oh, that's too complicated. I'm just going to take a picture of it again. Oh, it did not pick up the point. Here, do it this way. Let's try that. That time too. So it's 5.67. So obviously, it lost some energy because it hit the ground at that speed, came back off the ground that speed. The question is, what's the coefficient of restitution? The velocity of the Earth is equal to 0 and equal to 0. So then if you look at this, let's say B is going to be the ball and A is going to be equal to Earth. And then we'll grab this, and maybe what I'll do is just copy it. And I'll just copy it that way. So if I look at this equation, it became velocity A final, A is the Earth, 0 minus velocity of B final. And you got to pick a direction. So I'm going to, it doesn't matter which one you pick. So I'm going to make that positive. So that's 5.67 because it's a minus sign, and that's positive because that's positive. And so velocity of B initial is this. It's not positive, it's negative, 19.65. The velocity of the Earth before the impact is equal to 0. And so the coefficient of restitution for this is maybe a quarter, roughly. 0.2885. And so it's pretty low. So if you're on the tennis court, you drop that, then that's kind of what you see. If you dropped it and it stuck to the ground, like it had no bounce, it had a complete, came down, hit the ground, and just became a puddle down there, then this term would be 0, and then the coefficient of restitution would be 0. But let's look at the case where the coefficient of restitution is 1. Okay, the coefficient of restitution equal to 1 means that the velocity off the ground, okay, so I just copied this. Okay. If the coefficient of restitution was 1, here, we're in that realm. The only way that could occur is if this thing was 19.65. And that would give you this term, that would give you that this term would be 19.65, and the coefficient would be 1. Then what would happen is you drop the ball from 6 feet, it comes back up exactly where it is. If you didn't touch it, it would just sit there and bounce back and forth, and it would never dissipate its energy. In reality, what will happen is, you're going to get kind of like that over time and elevation. It's basically going to damp out to nothing. And so, I guess the closest thing you can get here would be like one of those super balls. Those are pretty, those have a lot of bounce to them. This is embedded in, and so I think I'll just go ahead and divert. Because if you embed NCAA basketball rule. Okay, so if you look at the NCAA basketball men's rule book, let's see, I'll just download it. Okay, I'm just going to download now. Anyway, you get in here, you'll find there's a rule book about the equipment. Let's see if we can find it. Men's court and equipment, page 15. That's a lot of pages. Am I on page? Okay, court and equipment. So you get down here, and there's a description. Division, free throw line. These are all 3-point. There's something about the ball. Padding. There's all the stuff there. Blackboard. Basketball. Size. Okay. Okay, that's the size and material. The ball. Okay. The ball shall be inflated to an air pressure. Okay. The ball shall be inflated to an air pressure that when dropped from a 6 foot measured from the bottom of the ball, it will rebound to a height measured to the top of the ball of not less than 48 inches when it strikes the least resilient spot, nor more than 54 inches when it strikes the most resilient spot. So out of that, you could calculate the coefficient of restitution. Now, what's weird is he talks about the dropping it from measured from the bottom of the ball, measured to the top of the ball. But he also tells you the circumference has to be a maximum of 30, minimum of 29. So you could go in, and I don't know that we have time to do it, but hey, what the heck. So if the circumference 2 pi r, I don't know what the radius is, but let's just say it's 30 inches. I'm sorry, the circumference is 30 inches. Radius, I'm just, that's got to be like 18. I don't know. Radius is equal to 30 divided by 2 pi. Hey, I wonder if this thing will do that. It's got to recognize pi. Maybe. It does. 4.77. And if you're looking for the diameter, that doesn't make sense. The circumference is 2 pi r, 30 inches. So if you wrap it around there, how big is the basketball? Okay, so if you do that, you multiply it times 2, then you just get 30 over that. That just doesn't make sense. Let's actually bring a basketball. 9.5493 inches. 9 inches. No way. What am I missing? It does. Okay. Let me go back and look at the rule book. The circumference of the ball shall be within a maximum of 30 inches and a minimum of 29. $30. 9 inches. No way. Okay. I'm going to bring a basketball tomorrow. Let me just put, okay. Now I'm really baffled. Can't be. That's what it says. Database 9.4. Really? Seems like it's like that big. Okay, basketball. 9. That's all it is? Am I just okay? Because that's tip to tip. Okay. Well, now I'm kind of confused. I want to go home and measure the basketball in my garage now. I thought it was bigger than that. But anyway, that's bizarre. Okay. I guess I've never. Okay. So anyway, so you drop it from 6 foot measured from the bottom, and it returns measured from the top. Yeah, I mean, I guess that's the reason you look at the rules and stuff, because they don't make good sense. So it's 6 foot measured to the bottom of the ball. Okay, I got that backwards. There's 6 foot measured from the bottom, 6 foot, and it returns height. What did it say? So I'm going to find the highest coefficient of restitution. Okay, measured Okay, measured to the bottom of the ball, and it will rebound to a height measured to the top of the ball of not less than 48, but more than 54. Can't be more than 54. So I'm going to make it 54 inches. So that I'm going to use this, the bottom, as the reference. So the velocity is equal to square root of 2gh, which, believe it or not, that's the same thing I had before. That's 19.65. 19.65. So over here, what I've got to do is 54 minus, what was it, 9, we'll just say 9.6 inches. All that divided by 12. That's how many feet that is. And so that would be really weird. This is going to be weird. 3.7 feet. That means the velocity is going to be 2 times 32.2 times 3.7. Take the square root. And that's going to tell me that, come on. That's going to tell me that it's 15.436. So the coefficient of restitution cannot be greater than 436 over 19.65. Or coefficient of restitution cannot be greater than 0.785547. And so that's from the college rule book. Now the way they're supposed to do that is the referees are supposed to go out before the game even comes out and check the air pressure in the balls and drop the balls down. Sometimes if you go to a game early, and if it's a very important game, they'll be out there doing that. The home team shall provide the ball. Okay, so if there's any problem, it's the home team's fault. The referee shall judge the legality of the ball, and they select the ball for use provided by the visiting team when the home team cannot provide a legal ball. Interesting. Anyway, so the moral of the story is if you pump your ball too high, your coefficient of restitution goes up, and then you're illegal. So that's not the problem I wanted to solve, but that's kind of a good fill-in. So we'll come back to this one to find out if we can. We haven't found out if we can cheat at pool yet because we didn't finish that problem. That's good enough. I'll call it a day. There's probably a pro tennis rule book. Tennis rules and regulations. I wonder if there's a book on it or rules. Oh. Tennis, rules of tennis. 2023. Okay, so if I go down to here, okay, so the ball in play. Wait a minute, ball touches the line. Okay, the racket, the ball, page 3. There's 1, there's 2, there's 3. Ball, if you need the ball in play too. They don't talk about I guess. Okay, the ball which is must comply with specifications in Appendix 1. Okay. I never looked at the rule book here. Appendix 1. Wait, is it? This is Appendix whatever. 9 or whatever. Appendix 5. Appendix 1, the ball. The mass, the weight, the rebound. Okay. What does that mean? Rebound fast, medium. Rebound from what height? Ball. The ball shall conform to the type of the table immediately. Okay, this ball will be pressure after pressure. Called the internal pressure that is no greater than 1 psi. The altitude in play at 4,000 feet above sea level shall be attained for 60 days or more, so they can acclimate it to the specific term. The ball is also recommended for high temperature. This ball is pressurized at high altitude. Here, the deformation shows a single reading along the perpendicular. No two individuals are different than 0.0. Okay, mass, rebound. Rebound from what height? Oh, here we go. Forward deformation, return deformation. What? What? That's such a small amount. Okay. Well, we can look at that later. Or we can do this. Coefficient restitution. Oh, I got the O. Okay. The coefficient restitution vary according to the ball. Use a tennis ball at the highest value. Oh, and then the cricket ball had the lowest value. Okay. So did I go to the... Okay, here we go. Oh. The normal drop test. Anyway. Yeah, I don't want to take that. Coefficient is a normal drop test. So the physics thing. Where is the... There it is. So there he's dropping it. And then does he have a table that tells us, yeah, this is great, but where is the... Okay, golf ball, mass and diameter, this is great, but that's not the coefficient restitution. Coefficient restitution drops, so he's got a little bit from, I don't know what he's dropping there, a sports ball with a steel target surface. Okay, golf ball, table tennis, hockey, cricket. Okay, anyway. So I'm wasting time now. So, okay. Yeah. So I took a tangent off into the field there.